Okay, good morning, everybody. Welcome for this new colloquium from the Severo Ochoa program here at the Instituto de Astrofísica de Andalucía in Granada, in Spain. And today we will have the talk by Dr. Pietro Zucca from ASTRON in the Netherlands. Good morning, everybody. Sorry. Welcome for this new... And he will talk about the radio eyes for the sun, Heliosphere and Ionosphere, status and plans for the SKAO era. Pietro will be properly introduced by Pepa Masegosa. So, Pepa, please.
Thank you very much, Pietro, for accepting our invitation. It is a pleasure for us. Fortunately, the PI of the Severo Ochoa project could not come today. So let me introduce you, CV. Dr. Pietro Zucca is a solar physicist and a space weather scientist. In 2017, he started a position of telescope scientist for low-frequency array LOFAR at ASTRON in the Netherlands and was promoted to associate scientist in 2023. He received his PhD in 2014 Trinity College in Dublin, following his master's degree in Bologna in astrophysics and cosmology. His research interests range from observing low-frequency solar radio bursts to radiosolar spectroscopy instrumentation, with a special emphasis on coronal mass ejection under shock and are presumably causing type 2 radio bursts. His studies include multi-wavelength observation and imaging, as well as LOFAR observation to reconstruct coronal mass ejection and shock location as measured from log-wave type 2 burst emission. Dr. Zucca is a member of the IAU Division E, Sun and Heliosphere, and has an interest in science outreach. He taught at the recent LOFAR Data School at ASTRON in April 2024. So, Pietro, the floor is yours.
Yes. Thank you very much for this very warm welcome. I'm really pleased to be here, and I would like to tell you a little bit about the radio observations that we are carrying, of course, with LOFAR, but with other SKA pathfinders for the sun. And so I will tell you a little bit what we can do. Why is radio emission important for studying the sun? We're going to then go through the challenges that we're going to find in the future. For example, the challenges that we have with recording such a large amount of data sets. So the importance of the pipelines and archival of the data. And I will also tell you about a little bit the possibility of using the monitoring for space weather research. So let's start a little bit with this idea of what we're going to talk today. We're going to pass from the sun, imaging the sun, taking information of the radio emission from the sun. With SKA, we'll be really passing from 50 megahertz up to 15 gigahertz, together from low and mid. At the moment, such an instrument with this type of frequency capabilities is not available. I will tell you a little bit about, of course, the possibility of studying solar physics phenomena, the corona, the atmosphere of the sun, the transients like the coronal magnetic fields, and the CME coronal magnetic fields as well, but also tracking the CMEs in the heliosphere. Also understanding the solar wind and the heliosphere, so the density and the speed of the solar wind, and ultimately also the ionosphere, the effects of what this solar activity is giving to the ionosphere. So this we keep it in mind as our journey from the sun to Earth. But to first give you a little introduction on what is the why is the radio emission giving us so much information about the sun, I want to start with a little cartoon explaining the solar and heliospheric radio emission. So here we have a very beautiful image in extreme ultraviolet from the Solar Dynamic Observatory. And we can see that on top of one of what we call an active region, so the region where a group of sunspots, an active region is, you have also in 3D the column of plasma on top of it with a certain structure. And you can see here that the plasma follows the magnetic field lines, is strapped on it. And you can see this pinched area, this area where we have what we call magnetic recognition. Now you can make a drawing in 2D, very simplified, about some of the active region. And you can imagine here that you have a loop, so a structure of the magnetic field that enters inside the board and comes outside, where the blue ellipse is. So we have a section of this, and you can see that at some point there are some regions of magnetic field lines directed in opposite directions, and there, if you have a change in the topology of the magnetic field, it restructures with this large eruption, which is a solar flare. A solar flare is very bright. You can measure it in, of course, many wavelengths, from gamma ray to radio waves. It is historically been observed a lot in X-ray, in soft X-ray. So it's defined also by the excess of this. But with radio, it's very beautiful, the amount of phenomena that we can follow. Let's say you have a recognition. The topology of the magnetic field changes, so you have acceleration of particles, and the particles can accelerate, can go downwards, and downwards they will glow in the microwave. So the electrons will spiral along very strong magnetic fields. The only region where the magnetic fields are strong in the sun is very close to an active region. And there they can glow in microwave. So all of these features we can we would in the future also observe with SKAO. But also you have acceleration of particles in the other direction. Some particles can escape along open field lines, like in this case, and they can produce radio emission of different types. For example, type 3 radio bursts are one of the most common types of radio bursts. They are electrons that escape from the sun, and we can see that they really cover a large frequency range, and they escape with a very fast drift. Another feature is this other type of radio burst. It's called the type 2, and this one is generated by a shock. So once the plasma detaches from the sun after, for example, a flare, you have a magnetized bubble of plasma that starts to move with a certain speed. If the speed is faster than magnetosonic speed or alphane speed, we can generate then a shock. And the shock there can accelerate again electrons, and these are glowing like type 2 radio bursts. You can notice this type 2 are more slow in the drift, and they have a lot of fine features in the spectra. As the density become then progressively lower in the corona, they also emit at lower frequencies. So by tracking the frequency drift, we can, of course, understand that the shock, the radio shock, is propagating outwards. But of course, with the imaging, we can track it and understand also the fine details of where these shock signatures are happening. Because in fact, we don't know very well all the physics that regulates these emissions. Where are they happening in the CME? And why it is important to understand these fine details is also because the region where it happens along the CME, it's very important to understand if it's connected or not to Earth. So to really try to understand this Sun-Earth connection, we need to get an eye on that. And radio emission is really powerful. Now, if we're looking in the future, so with the SKA era, using SKA low and SKA mid will really enhance the capabilities that we have now, because it really gives us a view from 50 megahertz to 350 megahertz for the SKA low, and then from 350 megahertz up to more than 15 gigahertz for the SKA mid. So you can imagine that we can cover the entire range of frequencies that brings us from the outer corona, the heliosphere, to the basically the chromosphere itself. And of course, there you can merge with the existing instruments. But now, of course, SKA is not only a solar dedicated or solar space weather dedicated instrument. We have to share it with many other working groups. So today I will explain a little bit about the solar heliospheric and ionospheric physics group, which I have the pleasure now to co-chair with my colleague Rohit. So let's start a little bit from my perspective. So I will tell you now a little bit about what we're doing, for example, with LOFAR, which is one of the similar pathfinders, at least for the SKA low. And then I will tell you also of the experiments that and the observations that have already been done with MeerKAT, which is the basically what will become, it's the precursor of what will become SKA mid. Now, with LOFAR, we have 6 different key science projects are called. One of these is the solar physics and space weather, which I have also the pleasure to co-chair. And so some of the results that I'm showing here are the results of many of these young people, PhDs and postdocs, and also many colleagues that is part of this KSP. Now, just to give you an understanding on how complex are in general the radio observations that we do for the sun, I will tell you a little bit about what we do with LOFAR. Now, with LOFAR, we have the possibility to use the core stations are called. The core stations are all located in the Netherlands, where they are with a maximum baseline of about 3 kilometers. And those stations are all tied up to the same clock. That means that we can form very sharp beams that we call tide array beams, and we put this raster of beams at the location of the sun. At the same time, we also use the remote stations together with the core stations that are already doing the tide array. We also use them simultaneously to do an interferometric image. That means that we point a beam also for interferometry around the sun. At the same time, we also use the international stations. All these international stations are there operated in what we call fly's eyes mode. So each station has a beam, which is an individual beam that is pointing. What we do is pointing about pulsars or quasars that are very close to the sun in line of sight, because they can tell you about the, for example, using interplanetary scintillation, or for example, dispersion measure or rotation measure from the pulsar. They can tell us about the heliosphere. They also repeated, which are more details again also with SKA low. So this is a little bit to give you the idea of the complexity of the type of data. Now, once we have done that, for example, with the LOFAR, we also focus on times where Parker Solar Probe or Solar Orbiter are in their perihelion. So that are the campaigns that we do. We observe every day for the full 8 or 9 hours that we have the sun. For example, in the summer even, we can go up to 10 hours of observations here, and we can then support those missions. And the other things that we do is also we keep the information for each station by keeping what we call the autocorrelations about the ionosphere. So we can also give you, we can really study with a simple, with one observing time, we can study from the sun to the ionosphere, giving basically data sets for multiple type of scientists. And that's also important when you're observing in telescopes like LOFAR or in the future SKA. You want to reach as many science cases as possible in one single observation. This is a little bit about the data set for the tidal array beam, which will be most likely also done with the SKAO. At least that's what we're aiming for. You have the possibility of forming these pencil beams. Each of these pencil beams will be sensitive to a specific area of the sun. And from the dynamic spectra, you can get out some spatial information. This type of files are quite large. You can imagine that you are talking about a very fine frequency and time resolution. You're talking even about milliseconds in the time resolution. So this is an enormous amount of data set. These are some of the tools that we have, and most likely will be repeated for the SKA low era, where you can have previews of the dynamic spectra and the emission where it is. Of course, then we are talking about the interferometric images. These are the classical measurement set. So you do an inverse Fourier transform, and you can get beautiful images. It is, of course, very complicated to calibrate these images because they are basically observing the sun, which is very variable, and also the usage of other calibrators. It's quite complex. So when we are thinking about the strategies for LOFAR low, we need to take into account all of this complexity. In terms of baselines, SKA low will be actually perfectly sufficient because we have found already with LOFAR that amplitudes more than 40 kilometers baselines for the sun are usually not present. This is due to the fact that the corona itself, the heliosphere itself, basically scatters and enlarges the radio sources. And so we cannot basically get finer resolution. But already to 40 kilometer baselines, those are sources that can be even 100 arc seconds, for example. So it's quite interesting to check. And in fact, here are some of these examples where you see the size of the sum of the radio burst at 130 megahertz, for example. So again, basically we have the beam shape. So if we have a larger baselines, we can even aim at finer structures. What I would like then to show you here is really the scan of the sun then that we want to achieve. This is from 25 gigahertz down to 24 megahertz. And you can see that basically with SKA, we could cover from 15 gigahertz down to 50 megahertz. So almost all of these images. But the difference is that these are with 1, 2, 3, 4, 5, 6 instruments, and only with the SKA low and mid, we are already covering that large frequency range. So that will allow us really to have dedicated observations to study this phenomena. Now, some of the examples of the importance of the physics, what we want to find. These were some observations of the quiet sun that, for example, we started with LOFAR. At these frequencies, even just reconstructing a simple shape of the spectrum of the sun was not completely done. But also the idea of the importance of exploring longer baselines. Here I compared it with an historical instrument which is still operating and is very useful for us. It gives us a lot of information about the sun. This is the Nancy radioheliograph. For example, the Nancy radioheliograph has baselines about 1.8 kilometers. But you can already see that if you have features like this, in this case there were many radio bursts of different types happening in the same event. When you are looking at LOFAR HBA, with the remote baselines, we're starting to have the resolution to distinguish these features, while with the Nancy radioheliograph, for example, we could not resolve So again, for the SKA, the importance of keeping a very nice pipeline that can calibrate also the larger baselines. This is a very beautiful animation prepared by Professor Gary that shows how scanning the corona from about 17 gigahertz in this case down to 300 megahertz. So more or less most of the range of SKA mid plus SKA low, we can go down to 50 megahertz. You can really get information from all the corona, from the high corona down to the chromosphere. Now, most of the radio emission that we see is in the sun is about plasma emission, but down, especially higher frequencies, where we can see that the magnetic fields are quite strong in the active regions, and we can also have gyrosynchrotron of, for example, cyclotron maser, etc. So really, you can track all of these different types of emissions. Now, again, the importance of SKA low plus mid is really to, together with other instruments that will remain operational, maybe with LOFAR or NWA, you can have the possibility to really cover these areas that before were not imaged. So, for example, from 350 up to 15 gigahertz is really going to be opening a new window that was explored, but quite little. And linking then the radio observation to the space mission that are also very important for us. Why do we want to cover such a large amount of frequency and hence amounts of heights in the heliosphere? Well, because we want to understand also the link between the closed magnetic field topology to the open magnetic field topology. So more or less up of 2 or 3 are sun radius, you have an open field topology, and that connects to the heliosphere, to the Parker spiral. So if you want to study where particles are accelerated and where they are injected in the heliosphere, that's quite important. This is an example that we are preparing recently with LOFAR. It's about the very fine details of a type 2 radio burst. Type 2 radio burst, as I mentioned before, they are shock signature. Here you can see the CME, the ejection from the CME. This is faster than the ambient Alfvén speed in some regions, and therefore it emits radio waves. Now you can see that for us, we need to use the LOFAR LBA and the LOFAR HBA to reach basically about 180 degrees. And then in this other area where we have a spectrograph or FE, we cannot do imaging at the moment. There are some, and this is important. So if we have SKA mid and SKA low, we can basically track the full propagation of this type of shocks. With LOFAR, what we have done, we used the information from the Nancy radiograph. But again, here we're talking about 1.8 kilometers baseline. So if we want the finer details, SKA low here would be quite precious for us. Now, just to understand why is this important to have such a also spatial resolution is for understanding the various fine structures. Like before, this type of shocks were described just a simple drift, even in when they were classified in the 50s, for example. But you can see clearly that there is a lot of fine structures. There are a lot of fine structures that we need to understand. And in this case, with LOFAR, we found out that some of these lanes, it's called a multiple lane scenario, are produced in different regions of the CME shock. So different regions are glowing because on those regions, we have the characteristics of the orientation of the magnetic field. The Mach number is such for allowing the radio emission. And here we compared it also, for example, with the density structure, and we can see that a different density of the corona they glow, of course, at different frequency, and therefore we get different lanes of emission depending on the density that the CME encounters as coming out. There are many ideas for that. For example, in this paper that we published again in 2018, we had also the idea to understanding the structures of the shock front by fitting the CME. Again, so the potential of the future observations with SKA that gives us also the lower, the higher frequency, so the lower region where this radio emission. This is another work from a colleague that we prepared also recently with Diana Morosan, which is co-chairing with me the KSP for LOFAR. And you can see again the variety of structures and the complexity of this radio emission. And with the LOFAR, we started to understand already the region where they're coming, but also the fact again that they are located in multiple lanes, in multiple locations of emission. So it's not before that the shock happens only in the apex of the CME, but it is completely complex. It's all around the shock front in different locations. Different locations accelerate particles. And they can have even different speeds, of course, of propagation. Diana here put the observations with LOFAR also in perspective of the structure of the magnetic field in order to understand where they are connected to Earth. So doing so also using other spacecrafts, including Parker Solar Probe, Solar Orbiter, and also Bepi Colombo to see where the particles reach that. So again, here the importance of continuing this type of studies, but also to go in details using the combined information from SKA Law and MEED. So in terms of other science cases, again, that we want to cover, I will tell you a little bit also these campaigns that we do to support the spacecraft. I mean, we can call it a little bit the golden era of solar physics in this moment for the amount of missions that are running. We have 2 missions on the same time, Parker Solar Probe and Solar Orbiter. They arrived the closest to the sun that an object man-made did before. So they really can see and stream information about the very low corona, where these energetic protons and ions are produced, but also where the structure of the magnetic field can propagate from the low part of the corona to the mid part of the corona. So these alpha waves and ripples of the magnetic field propagating up, possibly transferring the energy that will be help us to solve the problem of the coronal heating. So how the solar corona is a couple of million Kelvin, while the surface of the sun is only 6,000 Kelvin. So those mechanisms that transfer the energy, they are not fully understood. So this these studies, and in conjunction of LOFAR, SKA, and other pathfinders, especially SKA, MEED and LOW together. With this study, again, we used LOFAR to track electron beams using the spacecrafts and the radio emission from LOFAR. And again, if you're able to track then the emission at higher frequency with SKA MEED, you can really track it back to the source. With the SKA Low, we can start from 50 megahertz in this case. So we will see similar here. I plotted from LOFAR also here the average frequencies. So again, putting in context with models, it's not only anymore sufficient to just have only radio observations. If you want to study some event, you need to go to also employ models of the corona and heliosphere to put those radio emissions in context. Another example of the studies that we're going to be doing also with SKAO are the fine structures also of these radio bursts like type 3, and especially understanding the difference between the fundamental and the harmonic emission. You can see here, this is a type 3. It's called a type 3b when you can basically separate the fundamental and the harmonic emission. And you can see that the fundamental emission, given that this is produced at the same plasma frequency of the local corona, it's not, the radio emission is not coming directly to us, but it suffers of basically wave propagation effect. So you can see it's all patchy and all discontinued, while the harmonic emission is much smoother. You can see that comes back to us. Well, also we could study the location of these radio sources. So we can see that the fundamental emission is very erratic. It's moving. We cannot appreciate very well where the position is because it's suffering of this wave propagation, while the harmonic emission is quite stable. And so we can use it to study the kinematics of this event. And here also comes the advantage of having a large frequency range like SKA mid and low to have the possibility to observe fundamental and harmonic at the same time. All right, but I started with this scheme. We looked a little bit now on the sun, on the low corona with SKA low, what we can do with all of this fine resolution instruments, what we can do studying the properties of the fine scales. Now we pass a little bit about the heliosphere and the magnetosphere. Now the techniques that we will employ also for SKA, both low and mid, are using interplanetary scintillation, for example. So looking at how the solar wind and the heliosphere responds to radio waves coming from outside our solar system. Say, for example, in this case, you look at compact objects like quasars, very compact objects in radio. And what you would see in a specific station of SKA or other instruments is that this quasar will start to twinkle, will start to be to basically scintillate when the radio waves pass through the heliosphere and the solar wind, and it will have a certain pattern. Now, if you observe with another station with some kilometers apart, you will see that the same pattern will arrive, but with a certain time delay. Now, this time delay is telling you the information on how fast the solar wind is in the heliosphere. So you can reconstruct that. Not only you can follow the same quasar for a long time, for example, like in this experiment, and you can understand, in this case, if a CME, if a coronal mass ejection is passing through the line of sight where you're looking at the quasar, you can appreciate the increase of density and speed when the CME is passing. So this type of IPS technique with SKA will be very, very powerful. And in fact, we envisage to do even more than what we're doing, for example, with LOFAR or other pathfinders, to look at the density of the solar wind as well. So for us to really track all the material that comes out from the sun, especially CMEs or the solar wind itself. So really, really exciting times by using together SKA low and mid. Another possibility is to use pulsars. So as you know, pulsars have emit, at multiple wavelengths. And because of the presence of the solar wind and the heliosphere, they are dispersed, those frequencies. So in a word, the larger basically the larger frequencies are dispersed less. You can see here, so low frequencies are dispersed more. And therefore, by measuring the dispersion measure, you can understand how many electrons are dispersing this radio wave. And that's very important for us. We can check basically direct information about the density of the heliosphere. With this paper that we published, Caterina published in 2020, we checked at the pulsars that arrive closer to the sun as actually Earth moves in 1 year time. You can see the pulsar line of sight closer, and as it goes to occultation, you can see that the densities are higher. So you can really track the density of the heliosphere and the solar corona. So those are powerful. We can also compare these measures to models like Euphoria or, for example, Enlil, or the IPS tomographic construction that I showed there, and put all of this information together to construct not only the low corona where the radio bursts are happening, but also the structure of the heliosphere, the solar wind. So really powerful tools with SKA as well. Another important thing that, of course, you want to do is to use what is called the Faraday rotation. So as an electromagnetic wave passes through a magnetized plasma, basically suffers of Faraday rotation. You have a rotation of the vector that can be measured, and this rotation can tell us how strong the magnetic field is, for example, in the CME or in the heliosphere. So again, like really important proxies that we want to observe. Now, passing a little bit also from the SKA meet, I can tell you a little bit about the recent work that has been done. Colleagues like De Vojotti, Divio Beroy, and other colleagues have recently published some preliminary observations with MeerKAT. So here you can see really that you can get a beautiful high fidelity spectroscopic snapshot of the sun, in this case of 1 gigahertz. But really you can imagine how in the future you can scan from 50 megahertz from SKA low up to 15 gigahertz. That would be really unprecedented, the amount of information that you can get from the low corona to the mid corona. And really this work demonstrates of the quality also of the image that we can achieve when SKA will be completed. So we're really looking forward for this amount of details and detailed studies that we can do in the future. This is really just the beginning with the pathfinders, but we can really increase this. Of course, we need to have a complex observing mode that will be able to observe both with SKA low, SKA mid, which won't be at the same time, but it can be arranged as subsequent observations, for example, but also scanning not only the imaging, but using the beamform and using also the information of the heliosphere. Again, other things that we need to investigate, of course, is the ionosphere itself. So the quality of the ionosphere actually helps us to understand if we can already correct. We need to correct the imaging that we're doing for the effect of the ionosphere, but at the same time we can study how the ionosphere reacts to these solar and space weather events. So again, a beautiful example on how with the same observation we can also do so. Now, of course, once you are observing this type of data sets, you need to think that you are recording an enormous amount of data. We're talking about data that in the perspective of the SKA will not even be recorded anymore as raw measurement. You would have pipelines that would already reduce the data in real time to compress it, to extract only the information that needs to be then science ready and put into a data center. We cannot afford it anymore to just record the raw data. You can imagine that just with the LOFAR, if we are recording some of the raw data, we're going up to 7, 8, or even 9 petabytes per year. So the amount of data that you will record with SKA would be 10 times more, if not even. So pipelines, it's very important for us also to define this type of softwares. This is what we're doing, for example, at the moment with LOFAR. You have some pipeline that could run in the archive. You could extract only the information that you need from this specific data set, and you create a science-ready event. So you can see that if you just combine all the antennas from a single station, you have already something like 1.7 terabyte per second. This information that you cannot stream it. It won't be feasible in the SKA area, especially with this amount of data flow. So you need smart ways to already reduce that. So this important technological pathfinder for SKA, of course. The storing site that we have, for example, for LOFAR, in the area of SKA, there will be large science data centers that will take care of making this data ready for science and store it and make it available in archives for the users. Just to give you an idea, we're talking about more than 40 petabytes with LOFAR after reduction. So these are already reduced into, almost science ready types. So you really need to act immediately. So it's a big machine. You have a lot of antennas and telescope, but you have to have a big data center with pipelines that will be crunching the data always in real time. And radio astronomy is really big in terms of the data storage. It's some of the largest data sets if you even compare it with other large archives that are currently there. Now, the final and important topic that I want to cover is also about the possibility of doing some space weather science. So not only understanding how the sun works, but also understanding how the sun can affect us and how all of these phenomena can be impacting especially the space weather. So to do that, for example, with LOFAR, we took a full station of LOFAR and we dedicated to observing the sun and the ionosphere. We started with core station 32, and it was removed from the astronomical observation, and we started observing only the sun. And also Cassiopeia A for understanding the scintillation of the ionosphere, but also for calibrating the sun. Now, it is envisageable that it will be nice if also with SKA, especially SKA low, that we have the possibility to monitor the sun with a beam without interfering with the observing runs. So also this type of modes as co-chairs of the working group, we will have to present and show. These are the type of information that we get at the moment with LOFAR. Now we are transitioning from LOFAR 1. So LOFAR 1 will be shut down, and we are turning on LOFAR 2 that will last for the next 10 years, which will then collaborate with SKA low to reach, again, those lower frequency down to 20 megahertz. And we can observe, in this case, a solar radio burst and ionospheric scintillation with a single station. We also do the calibration in real time of the stations, etc. But just to tell you a little bit about the pipelines that are running, there are also filtering pipelines for RFI. In this case, you can see there was a lightning storm, a lot of lightning strikes that to emit they kind of corrupt our data set. But some of the pipelines now are already able to filter them and remove them from the imaging, as well as algorithms that detect in real time the presence of this radio bursts and make a list of it. And as well as using the radio flux to use them for some space weather forecasting ideas. Of course, this is not going to happen always as a monitoring for SKA, but this will enable us to the science and the study to create new of these forecasting models. So this is about 45 minutes now that I'm talking. So I'm giving you now a little bit of the summary of what we have said. So the radio emission is a great tool to study the sun in the heliosphere and also the space weather. SKA low and SKA mid in synergy with other existing observatories will increase our ability to observe these features, and also increasing frequency coverage from 50 to 15 gigahertz really allows us to understand in the same event a multiple variety of phenomena. Of course, we need to create pipelines for the imaging. At the moment, we're just scratching the surface of this full potential, even already with the pathfinders. So with SKA, we really need to be ready to absorb this enormous amount of data. We are not be able to store the raw data. We need to be able to already process it in the various pipelines that we run. And then, of course, we need to make this roadmap into making sure that also our community, the solar, the heliosphere, and the ionosphere, will be presenting all of those science cases to participate in the SKAO science and observing with that instrument. And of course, be ready to have the community of PhD, postdocs, and researchers able to analyze the data set, which are not easy. They are complicated, but we need to make them science ready and science so that users like us PhD students can easily use those data without spending a full PhD just understanding how it works. That sometimes with LOFAR that's the case. So thanks very much for your attention.
Thank you very much, Pietro, for this wonderful talk. So now the talk is open for questions. Please raise your hand, and Teresa will manage the questions. So, Teresa, you can manage.
Yes, thank you. I get the privilege to lead the questions because I'm Pietro's host, so to speak, even though this is a web colloquium. Maybe another time we can have you here in person as well. Thank you so much. I thought that was extremely interesting. This is so far outside of my own field. I'm aware of everything SKA, but I do observations on galaxies. So observing on the sun is very exotic to me and very interesting. So I'd like to open the floor for questions from the quite substantial audience we have here now. Let's see if there are any. Okay, I see a hand. I saw a hand. And if not, I can also start up with a couple of questions, but mine will be of the more naive level.
I think.
Manuel, yes.
I can't see. Okay, yeah, go ahead, Manuel.
Okay, thank you. Thank you very much for this interesting talk. I am familiar with the deeper layers of the sun, photosphere and chromosphere, and maybe I have a question which may be naive for you, but this, if I understand correctly, the radio emission is due to temperature, but black body radiation, because it can also be related to electron density through the plasma, the electron oscillations, also due to the cyclotron emission because of the presence of magnetic fields. So how do you know if a particular emission is given by this or that physical process? Or if it is something that comes from the background or something due to a burst, a shock wave, how do you know, how do you separate all the different processes?
Absolutely. This is a very interesting question indeed, because what you're saying is perfectly true that you can have, you're observing a specific frequency, but the radio emission may come with different mechanisms, right? So you could have, for example, the possibility of having some gyrosynchrotron, for example, from the legs of a CME, or even in the region of the flaring region. You can have cyclotron maser. You can have the plasma emission that happens also in the other. So the way that we do is that we check the how bright is the emission, and we also make a spectrum of it. So, for example, for the gyrosynchrotron, there were some observations even from the early 2000s with the Nancy radio heliograph, where the scientists at that time were able to take a spectrum, and then, of course, with the spectrum curve, you can recognize, okay, this is gyrosynchrotron, for example. For the plasma emission, we use the brightness temperature. So we have some ranges where we can recognize that emission can be only plasma. Some other possibilities is to know what is the strength of the magnetic field when they're coming in the region where the emission is coming. But you're right that sometimes some type of radio bars, especially, for example, type 4 radio bars, which is the radio emission that comes in the post-frail loop, where the magnetic field there is high enough that you can have a mix of gyrosynchrotron and plasma emission. And so it's quite complicated. So we need to be very careful indeed with disentangle these different emission mechanisms. Let's say that the majority, at least for low frequency, the majority of the emission happens in the plasma emission for the sun, because the magnetic field is not strong enough to sustain, for example, a gyrosynchrotron.
So if I understand correctly, then you have to make use of the different frequencies and then combine them to put interpretation.
Exactly.
And the different frequencies, they are observed simultaneously, they have to be sequentially. How is that done?
The different frequency, ideally, they need to be simultaneously, because you need to produce an instant spectrum, which will be the case of SKA low and mid. So also LOFAR, for example. At the moment, we can observe all the frequencies at the same time. We, for example, focus only on the low band and only on the high band, but in that small frequency range, we can have them simultaneously. LOFAR 2 will go with a low band and high band at the same time. But when SKA will be starting to operate, you will really get unprecedented large frequency range, from 50 megahertz to 15 gigahertz. Has never been done. I mean, you need to link 6 or 7 instruments together at the moment. They usually don't observe at the same time. So really, this will be so. Let's say it will not open something extremely new in each band, but the fact that you have all of them at the same time with such a large sensitivity and resolution, both in time and frequency, then it's gonna make open a new window in a way, because you're exploring it all at the same time.
Thank you. If I am allowed, just a last question. Are there plans to combine radio observations with other facilities to get or to combine the deeper and the higher layers of the sun to have a global interpretation of the solar magnetic field or the solar atmospheric conditions?
Yeah, absolutely. Multi-instrument will be still the key, even with SKA, even having such a large frequency in radio. You want to have also other proxies. For example, X-ray from satellites that are orbiting now, like Parker Solar Probe or Solar Orbiter. There are instruments like, for example, STIX that look at the very high energy of what's happening at the flare, how the flare pulsates, how the different fine structure in the time domain, but also in the spatial domain will link then with the radio. And this is just one example. Of course, you want to also have models. So from the magnetohydrodynamic, understanding how the magnetic field and the alpha speed changes in the corona to see where the radio emission is happening. So the way of now publishing a scientific paper will be really opening into the multi-expert area. You really need to be expert on many instruments and collaborate with a large group to advance the knowledge. If you focus on one instrument only, you often we are not able to explain the full picture. So yes, we will for sure opt on that. At the beginning, will be already amazing to have some observing time. As I show you, there are so many working groups already for SKA. So each group will submit, proposals. So we really need to be good into linking the multi-instrument approach if we want to obtain observing hours.
Thank you very much. And thanks again for this interesting talk.
Thanks very much.
We have a couple of questions from the IAA Solar Physics Group members here. First, Jose Carlos, you're up.
Yes, thank you. Thank you very much. And thank you very much for an interesting talk. I guess that, first of all, I'm a complete layman in radio astronomy, not even for solar physics. But I guess that polarization of light provides good diagnostics, and indeed you have shown in one of your slides the Faraday rotation that I guess it's used as a Faraday diagnostics. So I would like you to elaborate a little on that, and also in the plans that SKA has for providing other than Stokes I data. Okay, so Stokes Q, U, and V.
Absolutely. This is a really interesting question because, in fact, for example, with LOFAR, we used many years to improve the imaging pipeline already for Stokes I, for the solar observations. And now we're starting to use also Stokes V to understand how the fraction of circular polarization, for example. But if you want to do the studies of understanding the magnetic field of a CME, so you need to understand the Faraday rotation for a pulsar, then you really need to conduct these polarization studies. And one of the things that we notice with LOFAR is that one thing that we need to understand very well and correct for is the effect of the ionosphere. So you can imagine that in terms of Faraday rotation, the dense plasma of the ionosphere is dominant with respect of what you're seeing in the heliosphere. So you really need to have a perfect model of the ionosphere to remove this effect and then understand the excess of Faraday rotation, which is due, for example, if a CME is passing through. Well, we are arriving now with these fine resolution observations to use that information of the ionosphere to correct for those phenomena. With LOFAR, we're just arriving up. With SKA, then we really need to start immediately to have the observing plan also using those proxy of the ionosphere to correct for the observation. Not only for solar physics, but for all the other astronomers. In fact, that will be really a symbiosis when we are planning those programs of the SHI, Solar Heliosphere Ionosphere, to then use that information to correct the imaging also for the other astronomy. It is very complicated. And in fact, that's why the only reason why we have only 2 or 3 events where we were able to measure this Faraday rotation from a CME, because it's complicated and you really need to have a very good knowledge of the ionosphere to correct that. But yes, so SKA will observe in full Stokes, and the plan is also to have the calibration using the observations of the ionosphere to correct for those phenomena. Thanks.
Thank you. Thank you very much.
Thanks.
Thanks. Luis, you're up. You're
yes.
You're muted.
Yeah. So thank you very much for a really interesting talk. I have a question concerning the expected spatial resolution that will be achieved with SKA mid. And the reason why I'm asking this is ground-based observations of chromosphere and also the corona, the lower corona, have reached very high spatial resolution on the order of 0.1 arcsecond. And the images and the analysis you showed seem to have really low spatial resolution, right? But maybe this is because of the baseline. And the question is then whether SKA mid will be able to provide a much higher spatial resolution than current radio observations or not.
Absolutely.
To make them compatible with
absolutely
with the ground-based observations.
Absolutely. Otherwise, you don't gain that spatial information. Well, if you look at, for example, what the scientists working with the data at ALMA have done, because it's such a higher frequency, they can achieve also high resolution, right? With if you're talking about 1 gigahertz, the image that I showed from the colleague De Vojotti, it was indeed something about I think in the order of 50 arcseconds. I don't quote my number, but something quite large. But that is also because we are using, in that case, they were using only the MeerKAT, so which will be just the core of what SKA mid will become. So all of those other baselines will really shrink down the resolution quite high. So from what I know from the science cases and science books chapter that some colleagues are preparing for SHI, we are going to get into a possibility to have resolutions to be useful to compare with those instruments. Of course, you need to improve the calibration. And if you want to compare 1 gigahertz, it will be challenging. But if you go up to 10, 12 gigahertz, you're starting then to approach same resolutions that you can compare with those instruments. There are also techniques and simulations to simulate the data, of course, but also to compare with a lower resolution to try to gain information. But in general, don't look at the resolution you get with MeerKAT, because that's just the beginning. There will be many dishes at higher baselines, therefore you will get a much better resolution.
Okay, thank you.
Thank you. Any more questions from the crew here? I was looking at the YouTube page too. There doesn't seem too many comments. If you could hear our applause, I'm sure there will be a really big applause going on because you're good at that, but it doesn't really go through online. So just so you're aware, we all really enjoyed your presentation. And could I just end with a question, and with the risk of sounding a bit like a recruiter, but I know that the other science working groups are very welcoming towards having multi-wavelength expertise in their groups. I'm just going to assume that that's the case also for the solar one. You're nodding.
Yes, absolutely. In fact, I would like to say that whomever in the audience today or people that you know, the SHI working group for SKA is really open to all of these collaborations, especially even now we're writing some chapters for the new science book, and we are writing all the synergies, for example, with multi-wavelength approach or other instrument or cases. So please do write to me or Rohit. Have a look on Google, SHI working group SKA. You will get a page. My email and Rohit's email is there. Reach out, even if you think, oh, I don't know, just saying out my name and what you do. That's really already enough for us to understand and gather from the community. Because again, like the question I got before, without collaborating with the full expertise of scientists using different instruments, you don't proceed with science. You really need to merge those. Please do so. And even if you're interested in learning how to use data in radio for your own research, Even you can start now with LOFAR data or other pathfinders. We're really, really happy to do so and even do some joint work in collaboration.
Thank you. That's great. Yeah, and you can also contact me if you need to have you put into contact with Pietro. Thanks again. Thank you, everyone, for showing up.
Thanks again.
Thank you.
Thank you, Pietro, for this
Gracias.
interesting
Muchas
talk.
gracias.